So now we're doing chapter 1, section 2. Functions and graphs. From now on out, what I'm going to do, I'm going to give you guys all the examples we're going to do, I'll give you in a sheet so you have them there with you. But the printer wasn't working this morning, so I couldn't do it. I'll give it to you tomorrow. All right. The first thing we're going to do, talk about function. What are functions? A function is a correspondence between elements of a first set called the domain with elements of the second of a second set. Called the range. So that each element from the first set maps to one and only one member of the second set. This is one and only one. That's very important. Now, the reason we use the word map is this is how we look at it. We have two sets of numbers. This first one is called the domain. This second one is called the range. Domain is where you begin, range is where you end. That's an example of a function. The reason they use the word correspondence between elements of the first and second. In the old days, what is correspondence? What do they refer to when they talk about correspondence? What's that? No.
I think so. Starts with the R, right?
No. We use it, we get it every day. Is that? Mail, exactly. Mail is still referred to as correspondence. Basically, it's this. If I write a letter, can I send that same letter to more than one person? Nope. That's why they call it a correspondence. A writes a letter, one letter, it can only send it to one person. B writes a letter, only send it to one person. They can send it to the same person. I mean, A and B can both send the letter to one, but it just has to be one to one. Remember, we called the domain, those are the X values, and these are called the Y values. Example 1. Determine if this correspondence of this set. We have -6, 6, -3, 3, and 0. Is that a correspondence? Why? Yeah, because each one of the members of the domain only go to one member in the range. So it is a correspondence. It is a function. Here's the next example. Let's look at this one. Appointing president, George Bush, Clinton, Bush, and Obama. Supreme Court Justice, Alito, Breyer, Ginsburg, Kagan, Roberts, Sotomayor, Thomas. Does this represent a correspondence? Why? Yeah, because Clinton did 2 people, and Bush did 2 people, and Obama did 2 people. So it's not a correspondence. How about the last one? Example 2. Determine which of these following correspondence is a function. Years in which presidential elections occur. The set of presidents, the set of VINs, set of all PGA tournaments, the set of all golfers in the PGA. Determine whether each of the following correspondence is a function. The person elected. The year in which president election occur, the person elected. Is that a correspondence? Why? Only one person get elected, yeah. All automobiles produced in 2014. Each VIN number. Right, there's more than one car, but do each car have the same VIN? No, each car has only one VIN, and each VIN only belongs to one car. So that's a correspondence. So that one would be the set of VINs. The set of all golfers who won PGA tournaments in 2013. Tournaments won. Can you win more than one tournament in a year? Yeah, so that's not a correspondence because one golfer can win multiple tournaments, like Tiger Woods. He won them all. The set of all PGA tournaments in 2013. The winners of the tournaments. Now think of the set of all PGA tournaments. How many winners can you get in each tournament? 1. So is that a correspondence? Yeah. I know. These are complex when you read these. But this is how they'd occur in the real world. Is this a correspondence? Well, the years in which presidents only occur once, and we only have one president. The VINs, each car has one and only one VIN. The set of all professional tournament, one golfer can win more than one tournament. The set of all PGA tournaments, you only have one winner per tournament. So now we have, look at the next one, relation. A relation is a correspondence between the first set, the domain, and a second set. such that each member of the domain corresponds to at least one member of the range. What's the difference between that and function? One-to-one. Right, because here, each member in the X value, the domain, at least one person. So a range, or a relation, I mean, that's an example of a relation. Each member can correspond to at least one person. But they have to have one person to correspond to. In other words, I can't have a D down here doing nothing. D has to correspond with somebody in that set. Make sense so far? Example 2, or example 3, I mean. Here I'm going to give you some sets. Is this relation a function? Who says no? Everybody else says yes? No is correct. A function. Remember, each element of the domain can only have one member in the range. We have X and Y. That's the same thing as domain range. Yes. Yes. You have to have, yeah, because if I can't just have that, I can't have X. It has to be somewhere on that graph. So there has to be a Y value somewhere there. If there was the origin, then it'd be Y is 0. But it has to be on that graph somewhere. Yeah, it's hard to see on the mathematics part, but on a list, it's pretty easy. You can't just have somebody sitting there. They have to correspond to somebody. So
Now, I know that the X can't be, but can the Y?
yes.
Okay. That's what it's.
Yes, so this is not a function. But basically, yeah. So what you guys just said here is this is exactly the way you do it. If each X value is different, then it is a function. If X values repeat, then the Y values must be the same to be a function. Yeah, see, so since we have the same X values here, they have different Y values, it's not a function. Is that a function? Anybody? Yeah. Look at the x values. Are any of them the same? Nope. Since they're all different, it's automatically a function. Is that a function? For that same reason.
Because it's different value.
Because all the x values are different. Doesn't matter about the y values. The only reason the y values come into play is if the x values are the same. In other words, is that a function? Yeah. Do we have any same x values? Yes. Do they have the same y values? Same point, so it's the same thing. Right, that's all there is to it. Everybody okay with that? And then looking at graphs, it's a lot easier to determine if it's a function, and we'll get to that in a second. Notation for functions. The reason we deal with functions instead of just equations, an equation looks something like this. We know it's an equation because there's an equal sign. X is independent. I can pick any X I want to, plug it in there, then I can tell me the Y. So I say, for you to tell me what Y is, I have to tell you if X equals 3. If I give you an equation like this, I have to define what the X value is here. Once I do that, then you would, anywhere you see an X, you put a 3 and work it out. So the answer is 3, 11. It's a point on a graph. So instead of writing y from now on, we define it as a function. This is read the function f of variable x. In short, we read f of x. The name of the function can be anything you want it to be. It could be G, it could be H, it could be A, it could be B. Just don't use X though, because X is the variable. And the argument for the variable in the equation is inside the parentheses. These are the same thing. These are the same thing. Because y and f of x are interchangeable. But the way they're used is different. Remember, for this first one, I have to tell you if x equals 3, right? Then you'd plug it in there. Anywhere you see an x, you put a 3. But for functions, all I have to do is I define the variable inside the parentheses. That tells me anywhere I see an x inside the equation, I put that value. It's going to give us the same answer. It just looks a lot easier that way. Because now I can ask you anything I want to. It's a lot easier using functions than this. Because I have to say x equals 3, x equals 0, x equals -3. That's a lot of extra writing. Here, I just have to write f of whatever. So if I said f of 0, well, the function name is f, so I have to use this equation. What does my x become? Anywhere I see an x, I put a 0. 3 times 0 is 0, plus 2 is 2. This one's -3. Here's the equation. 3 times -3 plus 2. Positive times negative is negative. 3 times 3 is 9. 9 is bigger than 2, so the answer is negative. 9 minus 2 is 7. Any questions so far? What would that give me? No, it's m. Whatever's inside the parentheses is what I define as my variable. So I go to my, since I'm dealing with f, I go to this function. Anywhere I see an x, I put an m in its place. So it becomes whatever's inside the parenthesis goes in place of that variable in the equation. What if I give you this? Replace x with what? So it's 3a plus 2 plus 2. Because all I do is replace the x in the equation. 3 times a is 3a. 3 times 2 is 6. Plus 2, so it's 3a plus 8. And that's my answer. You could put anything you want to. You could put equations in there. You could put more functions. You could put whatever you want to in there. Whatever you put inside there changes that variable in the equation. Let's work those out. Look at the first one. So in the first one, it says go to the function f. What do we put in place of x? -2. So we have 2 times -2 minus 5. We do multiplication first. Positive times negative is negative. 2 times 2 is 4 minus 5. They're both negative, so the answer is going to be negative. 4 plus 5 is 9. What about this one? What do you do here? Yeah, go to the G, and where you see an X, put a 3. So it's 3 squared. 3 times 3 minus 2. 3 squared is 9. 3 times 3 is 9. 9 plus 9 is 18. Minus 2 is 16. Now this one says I multiply 2, whatever this event gives me. So I go to this first one, anywhere I see an X, I put a 1. I have to do this part first. 2 times 1 is 2, minus 5. Since 5 is bigger, it's negative. 5 minus 2 is 3. Positive times negative is negative. 2 times 3 is 6. So far, so good. With all that writing, no. So if there's a coefficient, you first have to find that value and then multiply by 2. Okay, in the fourth one. In the f function, I put a 3. So it's 2 times 3 minus 5. That's the first part. Minus 2. I go to the G. Anywhere I see an X, I put a 2. So it's 2 squared. 3 times 2 minus 2. 2 times 3 is 6 minus 5. 2 squared is 4. 3 times 2 is 6 minus 2. 6 minus 5 is 1. 4 plus 6 is 10. Minus 2 is 8. So this is underneath the parentheses. Negative times positive is negative. 2 times 8 is 16. 16 is bigger than 1. It's negative, since the signs are different. 16 minus 1 is 15. So the answer is negative 15. Just piece by piece by piece. Want to do another one? Okay, let's do another one. This one is example 4. F of x is defined as 2x squared minus x plus 3. Find these values. So the first one, so in place of X, I put a 0. So it's 2 times 0 squared minus 0 plus 3. That becomes 0, that's 0, so the answer is 3. Now it says put a -7, so it's 2 -7 squared minus X, so it's -7. So far, so good. So we gotta do now this one in part, so leave it. We have to do order of operations. -7 squared is positive 49.
So do you multiply you do it square first or do you multiply first?
Order of operations, exponents first.
Always explain.
Yeah.
I do it all.
Yeah, so you have to do the exponents first. Because what this really means, 2, let's say 7 squared. What that really means is 2 times 7 times 7. You have to multiply them out. So if you're gonna, you can't just multiply 2 times -7, because that's inside the parentheses to begin with. But it's also squared. So it's 2 times 49. The negative times negative is a positive. Plus 3. Two times 49 is 98. Plus 7 plus 3. 7 plus 3 is 10, so we have 98 plus 10, which is 108. You don't always have to go, since they're all addition problems, you don't have to go left or right. By commutative and the associative property, I can move them around. The next one, we have 2. In place of X, we put 5A. So I have to do the exponents first, order of operations. 5 squared is 25. A squared. Minus 5A plus 3. 2 times 25 is 50. A squared minus 5A plus 3. That's as far as I can go.
That exponent just stays there.
Well, but I can't, yeah, it's not like terms. This is an A, this is A squared. They're not the same, so I can't combine them. You have to combine like terms. Those are not like. So again, 5A squared means 5A times 5A. 5 times 5 is 25. A times A is A squared. Now, the last one's going to be more difficult because it's an equation we're putting in there. So we have 2A minus 4 squared minus A minus 4 plus 3. Okay. I don't, again, the way they set this book up, I told you from day one, I hate it. Because we haven't talked about this stuff yet. What did y'all do here? You can't distribute because there's a plus or minus in there. What this means, oops, A minus 4. What A minus 4 square means A minus 4 times A minus 4. We haven't talked about multiplying binomials yet. That comes in chapter 3. Again, but they threw it to us already. What we have to do here is multiply everything in the first parenthesis times everything in the second. FOIL, if you guys remember that from high school. So A times A is A squared. A positive times negative is negative. A times 4 is 4A. That does it for that one. Negative times positive is negative. 4 times A is 4A. Negative times negative is positive. 4 times 4 is 16. Combine like terms. Negative 4a, negative, they're both negatives. 4a plus 4a is 8a. You only change exponents if you multiply or divide. You only change exponents if you multiply or divide. If you're adding terms, you only, or subtracting, you only change coefficients. So 4 plus 4 is 8, and they're both a's. It's not a squared. A squared is from a times a, makes it a squared. So you only change exponents when you multiply. Again, this comes in chapter 3. We talk about it more. So this becomes 2 times a squared minus 8a plus 16. Get rid of the parentheses, so I have to multiply by 2. 2a squared, positive times negative is negative. 2 times 8 is 16a. Positive times positive is positive. 2 times 16 is 32. There's a 1 in front of here. If there's no number, it's always a 1. Negative times positive is negative a. Negative times negative is positive 4. Again, they do this in chapter 1, section 2. We haven't done all this stuff yet. So combine like terms, that's 2a squared. We have negative 16a and another 1, negative 1a, so they're both negatives. 16 plus 1 is 17a. 32 plus 4 is 36. Plus 3 is 39. And you think that's bad? Yes. This one? This one? Or? Because that's what's inside there. That's what's given. Because it's a minus 4. Remember, I put it in place of x squared. So whatever I put in there, I square it. So it's a minus 4 times a minus 4. So all I'm doing is I'm taking this equation right here and bringing it over here. Again, once we get to chapter 3, I'll show you all the shortcuts for this stuff. But for right now, we have to do this. And for that matter of fact, the next 2 or 3 examples, you guys haven't talked about yet. But it's, again, I don't like the way they've organized this textbook, but we have to use it. Or you still need it up there? The next section are graphs of functions. Graph the following. F of x equals x squared minus 5. F of x equals x cubed minus x. F of x equals square root of x plus 4. These graphs will make more sense once we talk about these functions. Because the only way you can graph these now is by plugging numbers in the equation. So for this first one, Let's start -3, -2, -1, 0, 1, 2, 3. Because whenever you get a function, there are 3 questions you have to ask. Can I use negative numbers? Can I use 0? Can I use positive numbers? So if I plug in -3 inside here, I get -3 squared minus 5. -3 squared is 9, minus 5 is 4. Then I put -2 in there. -2 squared is 4, minus 5 is -1. -1 squared is 1, minus 5 is -4. Zero squared is 0, minus 5 is -5. 1 squared minus 5. 1 squared is 1, minus 5 is -4. Four minus 5 is -1. 3 squared is 9, minus 5 is 4. So do you see a pattern here? Look at the y values. 4, -1, -4, 5, -5. Each of these represent a point in your graph. It's the X and Y locations. So our first point is at -3, 4. 1, 2, 3, 4. The next point is at -2, -1. Next one's at -1, -4. Then at 0, -5. Then at 1, -4. At 2, -1. At 3, +4. So our graph looks like this. And later on in this chapter, when I talk to you about the library of functions, we knew that the graph was going to look this way. Because that's the graph of x squared, a parabola. Do the same thing here. What you're going to see is you're going to have a graph like that. Because that's the cubic graph. We haven't talked about the rules here. You cannot have negative numbers inside square roots. The smallest number that could be inside here is a 0. So if I take x plus 4 and set it equal to 0, I start off at -4. That's when it equals 0. At -3, -2, -1, and so on and so forth, it goes like this. When x is 0, y is 2. X 0 plus 4 is 4, square root of 4 is 2. So plugging lesson, it's very time consuming. So you just have to plug in lots of points and then, but knowing which points, I cannot use -5 because you cannot have negative numbers inside here. We haven't talked about that yet. example 6. Here's the function. X squared minus 6. Find these two values. So the first one, anywhere I see an X, I put a -3. Anywhere I see an X, I put a -3 squared. -3 squared is +9, minus 6 is 3. Now I put a 1. 1 squared minus 6. 1 squared is 1 minus 6. Since they're opposite signs, take the sign of the bigger number and subtract them. 6 minus 1 is 5. Now, another way you can do it, if I give you a graph and I ask you to find f of -3, go to -3, go to the graph and see where the y value is. Same thing. F of 1, go to 1, go to where the graph is and see what y value is, -5. So if I give you a graph, you can look at that. And the x values are the horizontal, the y values correspond to where it is on the graph. So far, so good? Okay, last thing, then we'll let y'all go. Graphically, if I give you a picture, remember, when I give you a set of numbers, you always look at the x values. If all the x values are different, is it a function? Yeah. But if any x values are the same, they better have the same y values. This is what we call the vertical line test. If you draw a vertical line anywhere on the graph of the function, and it crosses the graph more than once, then it is not a function. If you draw a vertical line anywhere on the graph and it crosses the graph more than once, it's not a function. So again, if you have a picture, it's much easier, which goes with the same thing. Like, for example, is a circle a graph? Is a circle a function? Nope. If I draw a vertical line, I cross it twice. For example, let's say this value x is 3, and that's +2, and this is -2. Because the same x value has two y values, not a function. Okay, really quick, we'll just do these and we'll call it a day. Is the first one a function? Yes, because I could draw vertical lines, never touch it. How about the second one? No, because if I draw a vertical line here, I cross it 3 times. Is this one a function? No. Is this one a function? Is this one a function? Yeah. Is this one a function? Yes, because if I draw a line here, that I cannot use that one, I can use that one. That's what the open circle means in closed circle. So this one is a function. Not continuous, but it is a function. All right, so we'll call it a day there. Time of death, 11:07.